Atoms are incredibly tiny particles. They are so small that they cannot be seen with the naked eye, and even the most powerful optical microscopes struggle to reveal them. To truly observe atoms, scientists use advanced tools like electron microscopes, which can magnify these minuscule particles to a level where we can study their structure and behavior. They are the fundamental building blocks of everything around us. Every single object, whether it's a solid, liquid, or gas, is composed of atoms. These atoms come together in various combinations to form molecules, which in turn make up the different substances and materials we encounter in our daily lives. Imagine everything you can touch, see, and even smell. From the book you read to the plants in your garden, and even the water you drink, all these things are made up of atoms. Each object is a complex arrangement of atoms, bonded together in specific ways to give the object its unique properties. All of these things are made up of atoms. The way atoms bond and interact with each other determines the characteristics of the material. For instance, the hardness of a diamond or the flexibility of rubber is a result of how the atoms are arranged and bonded within the material. Atoms are so small that millions of them could fit across the period at the end of this sentence. To put it into perspective, if an atom were the size of a tennis ball, a typical human cell would be the size of a stadium. This incredible smallness is what makes the study of atoms both fascinating and challenging. Despite their size, they are incredibly important. The arrangement and type of atoms in a material determine its properties, such as strength, conductivity, and reactivity. For example, the difference between a piece of coal and a diamond lies in the arrangement of carbon atoms. They determine the properties of everything around us. The unique characteristics of metals, plastics, and other materials are all a result of the specific types of atoms they contain and how these atoms are structured. This atomic arrangement is what gives each material its distinct properties. The air we breathe, the water we drink, and even our own bodies are all made up of different types of atoms combined. Oxygen, hydrogen, carbon, and nitrogen are just a few of the essential elements that make up the molecules in our bodies and the environment around us. Understanding atoms is key to understanding how the universe works at its most fundamental level. By studying atoms, scientists can uncover the principles that govern the behavior of matter and energy, leading to advancements in technology, medicine, and our overall comprehension of the natural world. The study of atoms opens up a world of possibilities, from developing new materials to understanding the origins of the universe itself. While incredibly small, atoms are made up of even tinier particles. At the center of every atom is a nucleus. The nucleus is home to two types of particles, protons and neutrons. Protons carry a positive electric charge, while neutrons carry no charge, making them neutral. Orbiting around the nucleus are electrons. Electrons are much smaller than protons and neutrons and carry a negative electric charge. The number of protons, neutrons, and electrons in an atom determines what element it is. The idea of atoms has been around for centuries. Ancient Greek philosophers first proposed that matter was made up of indivisible particles they called atomos, meaning uncuttable. However, it wasn't until the 19th century that the scientific study of atoms truly began. Scientists like John Dalton, Ernest Rutherford, and Niels Bohr made groundbreaking discoveries that revolutionized our understanding of atoms. Their work laid the foundation for modern atomic theory and continues to shape our understanding of the universe today. In the early 1800s, English chemist John Dalton proposed his atomic theory, which became a cornerstone of modern chemistry. Dalton's theory stated that all matter is made up of atoms, which are indivisible and indestructible particles. He also proposed that atoms of the same element are identical in mass and properties, while atoms of different elements have different masses and properties. Dalton's atomic theory provided a framework for understanding how elements combine to form compounds, revolutionizing the study of chemistry. Section 5. Rutherford's gold foil experiment, unraveling the atom's secrets. In the early 20th century, physicist Ernest Rutherford conducted his famous gold foil experiment. This groundbreaking experiment would forever change our understanding of atomic structure and the nature of matter itself. This experiment involved firing tiny alpha particles, which are positively charged particles, at a thin sheet of gold foil. The setup was simple yet ingenious, designed to probe the mysteries of the atom. Rutherford expected the particles to pass straight through the foil, as the prevailing atomic model suggested that atoms were like a plum pudding, with positive and negative charges spread out evenly. However, to his surprise, some particles were deflected at large angles, and a few even bounced back. This was a shocking result, as it implied that the positive charge was not spread out but concentrated in a small region. This led Rutherford to propose a new model of the atom. He suggested that atoms are mostly empty space, with a small, dense, positively charged nucleus at the center. This nucleus contained most of the atom's mass. His model revolutionized our understanding of the atom's structure. It paved the way for future discoveries in nuclear physics and quantum mechanics, fundamentally altering the course of science. Rutherford's work laid the foundation for the modern atomic theory, influencing countless scientific advancements and technologies that shape our world today. Section 6. Bohr's Model Electrons in Orbit. In this section, we delve into the groundbreaking work of Niels Bohr, a physicist whose contributions to atomic theory have been monumental. Building on Rutherford's work, physicist Niels Bohr proposed a model of the atom in which electrons orbit the nucleus in specific energy levels or shells. This was a significant advancement from Rutherford's model, which couldn't explain the stability of atoms. Bohr introduced the idea that electrons travel in defined circular paths or orbits around the nucleus, and these orbits correspond to specific energy levels. Bohr's model explained why atoms emit light at specific wavelengths when heated. This phenomenon, known as atomic emission spectra, occurs because electrons absorb energy and jump to higher energy levels. When they return to their original levels, they release energy in the form of light. The specific wavelengths of light emitted correspond to the differences in energy between the levels. When an electron jumps from a higher energy level to a lower one, it emits a photon of light with energy equal to the energy difference between the two levels. This process is fundamental to our understanding of how light and matter interact. The energy of the emitted photon is directly proportional to the frequency of the light, which is why different elements emit different colors when heated. Bohr's model was a major step forward in understanding the behavior of atoms. It provided a clear explanation for the stability of atoms and the discrete lines observed in atomic spectra. Although later models have refined our understanding, Bohr's model remains a crucial milestone in the history of atomic theory. It laid the groundwork for quantum mechanics and continues to influence scientific thought to this day. Section 7. Atoms in action, forming the molecules of our world. Atoms are not content to exist in isolation. They are constantly interacting with each other, forming bonds to create molecules. A molecule is simply two or more atoms held together by chemical bonds. These bonds result from the sharing or transfer of electrons between atoms. The type and strength of the chemical bonds between atoms determine the properties of the resulting molecule. Section 8. Atoms, the building blocks of everything. From the smallest molecules to the largest stars, atoms are the fundamental building blocks of everything we see in the universe. The way atoms interact and combine dictates the properties of all matter. The diversity of the universe, from the air we breathe to the stars in the sky, arises from the interactions between atoms. Understanding atoms is therefore crucial to understanding the universe. Section 9. The enduring allure of atoms. The study of atoms continues to fascinate scientists today. New discoveries about the behavior of atoms at the subatomic level continue to push the boundaries of our knowledge. From the development of new materials to the advancement of medical technology, understanding atoms has led to countless technological advancements. As we delve deeper into the mysteries of the atom, we unlock new possibilities for the future.